Here we are going to discuss your transient response and your steady state response. If you have a systems, your system, for example, if you have a beam, okay, and you are able to identify what is the mass matrix and what is the stiffness matrix and what is the damping matrix, then we can write the dynamic equation of motion like this: mx dot mx double dot plus cx dot plus kx, that is equal to ft. Ft is your forcing function. Okay. Now, if you assume a force like this, okay, in that case, then this our solution is to be like this. Okay, where first part is corresponding to your transient response, okay, and second part is corresponding to your steady state response. Okay, steady state response. Okay. Now, if you want to plot, x, this, if you want to plot x, okay, with respect to time, you will observe that initially we are getting a response like this, and then after some times we are getting our response, where our response is very steady in nature. Steady in the sense the response which is a function of your function, which is a function of your forcing frequency. Here you can see that part is your C1 sin omega t and C2 sin omega t. So is your omega is your frequency of forcing function. Omega is your frequency of the forcing function. Okay. So in the steady state response, our system response become a function of forcing function or forcing frequency. Okay. So in the steady response, it will be a function of forcing frequency and is to continue for longer duration of time. The transient response is to stay for shorter duration of time. Since it is stay for a shorter duration of time, we used to call that is your transient response. Okay. Another part is here, is here, is here. That is corresponding to our steady state response. Okay. Adjustment is a function of forcing function. Here is this part is just the corresponding to your steady state response, and here you have C1 and C2, that is on constant. Okay, and here you can see that is your omega. Omega is your forcing function. So steady state become a function of forcing frequency. Okay. Now, if you want to plot steady state response and the total response, you will observe the total response initially used to have some disturbance. Okay, for few time, for the initial few seconds, and then our total response is to matches with our steady state response. Okay, basically after some times our total response of the systems become a function of the forcing frequency. Okay, so in the initial portion, the response we are getting, which is to stay for shorter duration time, which to say that response is your transient response. Okay, now if you want to plot the steady state response in the time domain, you want to plot a steady state response in the time domain, our steady state response will be look like this. Okay, that is basically function of our forcing function. Now, if you want to plot the steady state response in the frequency domain, you will get a graph like this. Okay, so in the frequency domain, in the x-axis we will have a frequency. Okay, that is omega by omega n, and here we will have the amplitude. Okay, here we will have the amplitude. Okay, now here we will observe that that our magnitude of displacement, okay, can be written in this form. Okay, now if omega, that is your forcing function, okay, omega, that is your frequency of forcing function, omega, that is the frequency of the forcing functions, is equal to omega n. Okay, in that case this part is coming to be 0. Okay, and if the system do not have any damping, then this part also is to be 0. So here amplitude will be too high, or here the amplitude will be infinite. Okay, so that infinite we can represent like this. Okay, which is a large amount of displacement. Okay, damp system, so J is equal to 0. Okay, now if you have a system, if we have a system where you have little bit damping, you have a system where you have a little bit damping. Okay, in that case, J you can assume some sort of damping factor here. You can assume 0.01 like that. Okay, and if omega is close to omega n, when the forcing frequency is close to your natural frequency, we know we used to get resonance. Resonance in the sense we used to have a large amount of vibration when your forcing frequency very close to your natural frequency. So here you can see when our forcing frequency is coming close to our natural frequency, we are getting large amount of displacement. Okay, initially we have displacement like this. Now we have large amount of displacement. Okay. Now since there is damping, then we can restrict our magnitude of the vibration. Okay. Since there is a damping, or if you have a damping, then we can restrict the magnitude of the vibration. Okay. Now if you increase the damping, you will observe that our magnitude of vibration is to be very low. Okay. So this is basically your transient response and your steady state response. Again, in the case of transient response, if you do not consider any damping, then our displacement, okay, will be function of, or displacement will function of, or you can say displacement will be, there will be only steady state. There will be only steady state response. Okay, we will get this solution only because this J will be 0 here. Okay, so in that case, we will get a displacement which is a function of your forcing frequency. Okay, so here in the ABAQUS, we will see how we can obtain transient response. Okay, first we'll try to obtain response for a undamped systems, and then undamped systems, and then we'll try to obtain our steady state response for a undamped case, and then we'll try to increase the damping, and we'll see whether we are getting this type of graph or not. Okay. Here first we are going to perform time history analysis. Then we are going to perform modal analysis, and then we'll perform our steady state analysis. Okay, so to do our time history analysis, what we are going to do here, we are going to make a simple cantilever beam. So here I make a beam of 1 meter length, and then I define the property. So here in the material property, you can see I just define modulus, Young modulus, and Poisson ratio. Now here I have to define density since we want to perform our dynamic analysis. So here I need to define density. Density of the steel is 75 kg per meter cube, and property of that the steel, or Young modulus of the steel, 100 GA, and Poisson ratio consider 0.3. Okay, and here define a cross section here. The cross section here, if you see from the file, you can see we have defined this your 15 and depth 10 mm. And thereafter we have assigned it. And next, what we define the assembly. Here we have created instance, and then we have defined. Okay. Next, what we have done here, have done here. Next, we have to apply. Next, we have to assign what type of analysis we want to perform. Okay. Next, here we have to assign what type of analysis we want to perform. Here I am going to select dynamic implicit. Okay, and time period I can make it for 5. Increment here I can mix peak type. Increment here I can mix fixed type, and increment size I can make it 0.01. Number of increment I make 5,000, and increment size 0.01. Okay, and here, okay, so here we have defined the step. Now what we have to do? Now what to do? You have to apply the loading. So here we will apply loading at one end, that is your 10 kilonewton. Okay, one end will apply 10 Newton load. At one end will apply 10 Newton load, and loading type is instantaneous. Okay, so here we're going to see how the response is coming. Now in the other end, what we're going to do, we are going to make fixed conditions. So here we will choose MCaster option. Here we will restrain all the degree freedom. Okay. Now what we can do, we can submit the job. So here what we are going to do, we are going to create the job, and here we are writing your dynamic, and here we can write implicit, and that is your undamped case. Okay, undamped. Dynamic, implicit, undamped. Okay. Now what we're going to do, we are going to submit the job. Okay, sorry. So next what we have to do, here we have to list output, we have to request for the output. So before going to that, you have to go to tool, and you have to create a node set. So here node set, you can write n node, and here we can select it. Okay. Now what we have to do, we have to go to the step, and here we have to request for history output. Here instead of whole model, here select set, and here you write n node. Okay, and here increment, you just write each increment n is equal to 1, and request for displacement, that is your u2. Now what we're going to do, we're going to submit here. We're going to submit job here, so submit it. Okay. So here you just see, okay, we are analyzing a undamped systems. Undamped systems with a load of instantaneous load. Now since system is undamped, there will not be any transient part. Okay, so next run, we are going to introduce damping so that we can get transient as well as your steady state response. Whatever the response here we will get, that is your steady state response. Steady state response that corresponding to your instantaneous loading. Okay. Job is completed. Now what we can do, we can go to your history output. Here we can ask for result. Here you can see we have requested for 5 times. Okay, 5 unit of time. We have requested for 5 unit of time. So we are getting some response, and we can save it. That is your undamped response, undamped instantaneous. Okay. So this response is corresponding to your steady state part. Now what we're going to do, we are going to introduce damping. So here in the material property, we can add damping. Here you can see damping is there. Now here we have to give some value. You have to give some damping value. So the damping value we can introduce in terms of alpha and beta, that is corresponding to your proportional damping or relay damping. Okay. For example, here we are considering alpha, that is your nearly 0.2. Okay, and beta we can write 0.002 like that. It's just observe. We don't know how much damping will be. Okay, so here we just assume some arbitrary value to get a damped response. Okay, so this alpha and beta, that is corresponding to your alpha m C matrix, that is equal to alpha m plus beta k, that alpha and beta we are providing. And ABAQUS already calculated mass matrix and the stiffness matrix. So now here if you introduce alpha and beta, ABAQUS can calculate the damping matrix also. In the next video, I already explained. In the next video, I'll explain how we can calculate alpha and beta, what is the significance of it, all the things I'll discuss in the next video. Because for the time being, you just assume some value of alpha and beta so that we can get a damp response, and we'll see how the damping is affecting our transient response. Okay, and how the damping is affecting overall our total response. Okay, so here we are providing damping in terms of alpha and beta. Now here what we are going to do, we are going to summarize this job 2. Okay, and we are going to see how the damping is affecting our time response. Now job is completed. Here we can see how damp time response look like. Here you can see this is our damp response. Here we can save it as your damp response. Okay, and now what we can do, we can compare this one undamped and damped. Okay, so here you can see how damping is affecting our time response. Here you can see only we have changed the damping. Rest of the thing are same. We have the same instantaneous load. We have the same metal property, same dimension, all the things. Okay. So here you can see how damping is look like. So here in this case, the total response is combination of transient response as well as your steady state response. Okay. Now what we're going to do, we are going to change the loading. We're going to change the loading as a periodic loading, and we are going to see how our steady state response and our transient response is coming. So now what we're going to do, we are going to change the loading here in the loading part. What we can do, we can modify the loading here. We can modify the loading instead of your instantaneous loading. Here we are going to apply as a periodic loading. So here in the periodic loading, here I have to write what is the circular frequency. So I know for this case, circular frequency is nearly 8 Hertz. The first circular frequency is nearly 8 Hertz. So I'm writing 8, and I'm writing your starting time is 0 and initial amplitude is 10. And this also is 10 and this one is 0. So basically this is corresponding to A sin omega t plus B cos omega t. So B I'm making it 0. That means our forcing, our force is a function of sin omega t. So force F, that is equal to A sin omega t. Here A is 1, and you just remember that I already applied the magnitude of 10. So basically 10 sin omega t, that amount of force we are applying here. Okay, so here instead of instantaneous, I am selecting amplitude here. I click it here, okay, and now I am going to submit the job. So here again you just see I just changed only the type of loading, and we are going to see how our response is coming, how our transient response as well as your steady state response is coming. That we're going to see. Now job is completed. Now we're going to see how the time response is coming if the load is our sinusoidal load. So here you can save it as your sinusoidal. Okay. Here you can see this part, initial part is corresponding to your transient part, and then our displacement is a function of periodic force. Here you can see this initial part is a function of, here you can see the initial part we are getting some transient response plus steady state response, and 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 as the time increases, you can see now our displacement is a function of forcing functions. Okay, so initial portion here we have transient part plus steady state part, but as the time progresses, transient part is to vanish, and then we are getting a displacement which is a function of forcing function. So displacement is also your coming as a sine function. Okay, since we have applied a sine force and we are measuring in that loading point, so loading point also should show a sinusoidal type or type of displacement. We are getting that amount of that type of displacement here. So as per our understanding, it is correct because we have applied a sinusoidal force at the end, and we are also getting a displacement pattern which is sinusoidal in nature. Initial portion we have some some pattern which is corresponding to your transient part plus steady state part, but after some time transient part vanishes and we are getting a sinusoidal response. So this is the way basically it should correlate our response as well as steady response. Now we are going to see how we can perform this where our displacement is a function of frequency. Here displacement of time. So once we want to plot response, there we will observe the displacement is a function of. We are going to see how the displacement look like. That is come as per our agreement or not. That are going to see. We are going to perform modal analysis here. What we are going to do? We are going to do linear perturbations. Okay, and here the selecting frequency to have our frequency analysis, to have our modal analysis. So here I am selecting 5 eigenvalue, first 5 eigenvalue. Since we are providing boundary conditions, so we will not have any rigid body motion. All eigenvalue will be positive. Now here again we have to apply the boundary condition, and the boundary condition so will be your fixed boundary condition in cluster option here. Now what we are going to do, we are going to submit the job again, but I am going to rename it as your modal analysis, and we are going to check what are the frequencies are there. Okay, so once we perform modal analysis, then we will go for steady state analysis. In the steady state analysis, you will observe that steady state analysis is of two process. Okay, steady state analysis is consists of two processes. First, we will perform modal analysis, and in the second step, in the first step, we will perform modal analysis. In the second step, we will go for steady state analysis. Okay, so here we are going to see what are the frequencies are there. 8.15 Hz. So this is the first mode. Second mode shape is of 14 Hz. Then frequency is of 14 Hz. Third one is of 51 Hz. And fourth one is of 142.78 Hz. And fifth mode is of your 251.88 Hz. Now here you can see, since here you can see what are the mode are there plane. So here you can see what are the mode are there in our XY plane. So this is the first mode which is coming in our XY plane. Second mode is not in the XY plane, it is in XZ plane. Now this is third mode. Third mode again is our XY plane. Fourth mode also in our XY plane. Fifth mode again is not in our XY plane. So second mode and fifth mode are not in our XY plane. Okay. So here we have learned that if we perform modal analysis, we will get our frequency and the mode steps. Okay, now we will go for steady state analysis. So here in the step, what we are going to do? We are going to create one more step. What we are going to do here? We are going to perform steady state dynamic analysis. Steady state. So here in the second step, what we are going to do? We are going to select steady state modal. Okay, now here it is saying use frequency to subdivide each frequency range. So here I am writing lowest frequency is 1 and upper frequency is your 250, number of 120 and 3. Now damping here, you can see we have direct damping. Here it is saying that how much damping you want to apply. First mode, okay, first mode is your 1, end mode is your 5, and critical damping is of your damping fraction. So here we can write 0.01 or 0.01. Here we can write 0.01. Okay. Now what we are going to do? We are going to apply the loading here. We are going to apply the loading here. So here we have selected the load is real in nature. Okay, there is no complex part in the loading, and amplitude of loading is instantaneous. Okay, amplitude of the loading is your instantaneous. So here what we are going to do? We are going to analyze it now. So in the step, what we have done? First step we have performed frequency analysis, and second steps we are performing steady state dynamic, which is modal in nature. Okay, now what we are going to do? We are going to submit the job, that is your FSD. Okay, now we are going to submit it, and we are going to see how the displacement is coming. Okay, one more thing we have to provide. One more thing, so we can do one more thing. We can do in the step. We can request displacement of set to. Okay, displacement of set, displacement set, and here we can put U2 here. Okay, so here we have requested displacement. Now again, what we can do? We can again submit it, and we can see how our steady state response is coming. Now job is completed. Now go to history output, or you can go to deep output also. And now we can go to your history output, and you can plot U2. Okay, so now here we can see our first frequency is coming nearly at 8 Hz, and second frequency is coming nearly at your here you can see first frequency nearly 8 Hz, second frequency is nearly 51 Hz. Since third frequency is out of plane, okay, and we have applied the load in that XY plane only, not in the Z plane. Okay, so we are not getting any peak here. Okay, we are not getting any peak corresponding to your out of plane mode. Okay, so third frequency here it is showing nearly at your 142, like that. The output, and select this one. You can save it as your magnitude there. Absolute
we can plot. Okay, so here we can plot as absolute value. Now here we can change the color. We can change this one to red. Now here you can see, if we enlarge it, here you can see the frequency here, first frequency here, and this frequency here, 7.88 we are getting, and then we have an anti-resonance point. We have a an anti-resonance point. Okay, so now like that. Okay, now what we can do, we can
In ABAQUS, we already obtained a graph like this. Okay, and there what we have done, initially we have considered a undamped case. Okay, initially we consider undamped case, and then we increase the damping, and we have observed that our magnitude of vibration is very large in case of your undamped case. Once we increase the damping, then our magnitude of vibration is getting reduced. Okay, and magnitude of vibration is coming to be very large when our forcing frequency is very close to our natural frequency. So here what we observe, that when forcing function is close to our first natural frequency, we are getting large amount of vibration. Okay, and in the second case also, when forcing function is close to our second natural frequency, then also we are getting one small peak there. Okay, that basically indicate our indicate that magnitude of vibration also is very high, but that is low in comparison to our first frequency. Okay, so that's why our in our dynamic systems, we will observe that first few mode is very important. Okay, so
step 1 will be linear perturbation frequency analysis, and my first 5 frequency we are interested in. Next, the second step, we are going to analyze steady state model. So now here, okay, lower frequency I am giving 1, and upper frequency I am giving 250. That is because of your fifth mode was coming as the frequency of the fifth mode also was 251. Okay, so I have just asked upper frequency as 250. I can write as 255 also. Then we can include the fifth mode also. Okay, so here we have done in step 2, that is your steady state dynamics. We have to give request at the step 2, and here we will select displacement. Okay, here it is saying every increment n is equal to 1. It's fine. Here we will ask for u2. Should do the modal analysis on the real structure without any loading, because modal analysis, if you see the equation, that is your m square, that is your omega square m is equal to k. Okay, omega square m is equal to k, so omega is equal to root under k by m. Okay, so if you see the modal analysis, in the modal analysis we used to solve that equation, that is your omega square m is equal to k, so omega square is equal to k by m, and frequency omega is equal to root under k by m. So here there is no role of force. Okay, so here we need to solve for actual beam with the boundary conditions. Okay, and in the second step we are providing a load there. Okay, and load here we are providing as a instantaneous load, and damping here we are not considering any damping. Okay, for the first case we are not considering any damping, and in the loading what we are going to do, we are going to apply concentrated force. So here, and magnitude here, that is value, minus 10 we are providing, and it is your instantaneous, and we don't have any imaginary value here. Okay, next boundary condition will be of your displacement type boundary condition. Otherwise, what we can do in the step one, we can provide the boundary condition in the step one. Okay, in the step one, we are providing the boundary conditions here, and we are restraining all the degree of freedom. Okay, so here we have applied a unit load in the step 2, and we have applied boundary condition in the step 1. Now here what we are going to do, we are going to see how the damping is affecting our steady state response. Okay, so we have done the part, we have defined your property, we also have defined your meshing, loading, all the things we have defined. Now what we are going to do, we are going to submit the job, that is your steady state dynamics. Okay, no damping. Okay, now we are going to submit it. Okay, now what we are going to do, we are going to submit the job. So we are submitting the job where there is no damping. Okay, once you submit the job, you can plot the graph. Okay, so here in the step, you just see we have done 2 steps. First step, we have performed modal analysis, and we have observed what are the frequencies are coming. So we have observed that first frequency was coming at 8 Hz, and fifth frequency was coming nearly to 51 Hz. Okay, in the step 2, when we perform steady state dynamics, there lower frequency I kept 1, and end frequency or upper frequency we are keeping it as a 250, so that all 5 mode can be included there. Okay, now what we can do, we can go to the result. Okay, and here we can see this output, here we can plot. Now here you can see this is the graph, displacement graph for your no damping cases. Okay, so now what we can do, we can save this data, so here we have saved the data, absolute value. Okay, next what we are going to do, we are going to introduce damping. So in the step 2, here damping, we are going to introduce. Here first mode is that 1, and end mode is your fifth, and critical damping fraction here I am writing at 0.1. Okay, or 0.01. Okay, now what we are going to do, here we are going to submit it again. This type of repetition we have to do for different damping value, 0.01, 0.02, 0.05, and 1, or 0.1. Okay, 0.1, and we will run the job and we'll try to plot it. So what we did here, here you can see we have that value xy data, we have xy1 data. Okay, so now what we can do, we can, so here we are going to get the data as xy data or amplitude, since we already have plotted as amplitude. Okay, so now we can we can extract the data in Excel. So here I can click OK. Your XY data 1, so here you can see we have one Excel data. Okay, so this is for our XY data 1. Okay, so next what we are going to do, we are going to see the response with damping case. Okay, so here we have provided damping as a fraction of 0.01. Okay, now here we will try to plot that U2. Here you can see we have damping, and due to that we have this type of response. Okay, now what we are going to do, again we are going to save this data U2. Now again we are going to save this data as absolute value. Okay, now here you can see we have this type of displacement. Okay, you can say that is your absolute displacement. Now what we are going to do, again we are going to extract the data as Excel sheet. Okay, as Excel data. Now here you click OK. Here again we will extract the data in Excel. Okay, now we have one more data set, that is your XY data 2. Now what we are going to do, again we are going to increase the damping. So here instead of 0.01 we can write 0.5. Okay, and we'll run the job. One more thing we will do, we will run for one more trial, that is your 0.1. Okay, damping as a 0.1, and we'll see how damping is affecting our steady state response. Now analysis is completed. We will go to our history output. Again we will plot our data. Okay, now again we'll save it as your absolute value, and again go to the plugin, and then we will extract the data. Okay, next what we are going to do, we are going to change the damping again. Here we will change the damping, that is your 0.1 damping fraction, and again we will submit the job. Okay, so in the meanwhile what we are going to do, here we will try to identify where we are getting anti-resonance point. So here you can see this is the peak, okay, resonance peak, and here this point, below this point here, that is your anti-resonance point. Okay, so what we are going to do, we are going to delete the data, and we will see how that our response look like. So in the steady state response, what we have done, we have basically created two steps. One step is your frequency analysis, that is your modal analysis, and here we have requested for 5 modes. And in the second step, what we did, we have applied a unit In the second step, what we have done, we are basically providing your, in the second step, that is your steady state dynamics. Here we have given our lower frequency as 1 and upper frequency as your 255. That upper frequency is based on that your mode number. Okay, so here you can see in our modal analysis we have observed that first frequency is your 8 hertz, nearly 8 hertz, and your fifth frequency was nearly 250 hertz. So I have given the upper frequency is 255 hertz. Okay, so what ABAQUS will do, that ABAQUS will basically take this frequency range to plot your response. Okay, and what we did, you will observe that in our loading case, you will observe that boundary conditions we have provided in the step 1. Okay, and that also propagated to the step 2, and boundary condition in terms of your displacement type boundary conditions. Okay, and if you see the loading, okay, if you see the loading we have provided in the step 2. Okay, so here you just see what we have done. Basically in the step 1 we have conducted modal analysis of our actual structure, and in the second step we have provided one unit load, and we have one load, we have provided one load. Okay, and we have performed our steady state response with steady state response within a range, steady state response within a range. And what we did here, we have changed the value, we have changed the damping value. Initially we have made damping value as 0.01, and then we have changed the damping value 0.05, and then we have changed the damping value to 0.1. Okay, so initial first data, what we have done, initial data, that is your first analysis, that is corresponding to our XY data 1, that is corresponding to our undamped systems. And then in the undamped systems, what we did, in the undamped systems we did not use damping value here. Okay, in the damping system we use that, in the undamped systems we do not use any damping value here. Okay, and damped systems we have used different damping value. So we have 4 data, XY data 1, that we have created for undamped systems, and then we have created XY data 2, that is corresponding to 0.01 damping factor, and XY data 3, that is corresponding to 0.05 damping factor, and XY data 4, that is corresponding to 0.1 damping factor. Okay, that is a 0.1 damping factor. Okay, so what happened, what we have done, once we complete the analysis, we went to our XY data. Okay, and here we select ODV history output, and then I click continue, and then we have saved this data. Okay, so like that, save data as a XY data 5, and we have saved it as a absolute value. Okay, this is our absolute value. Next, what we did, we went to plugin, and then we went to tool, and then here we select XY utilities, and we extract our data as XY data. Since already we have plotted as amplitude, so we are extracting as a our XY data, and here we have selected data 5. Okay, and we have basically created Excel file. Okay, similarly we also have created for XY data 1, XY data 2, XY data 3, like that. Okay, so we have 4 data set, that is corresponding to undamped systems and damped system. Damped basically, that is your 0.01 damping factor, 0.05 damping factor, and 0.5 damping factor. Okay, now what we are going to do here, we are going to see how the result is coming. Here you can see this is a frequency, x-axis is frequency, and y-axis is your displacement. And here you can see this point is your resonance point, and here we have anti-resonance point. Since this value is coming, now what we are going to do, we are going to delete that anti-resonance data. So what we are going to do here, we are going to see at which point we have that anti-resonance point. Okay, so 7.84. After 7.84 we have anti-resonance point. So where we are going to delete this data. Okay, now we have one data set where all magnitude are. So now we have XY data set 2. Okay, XY data 2. Now we have XY data 2. Okay, and similarly here also we are going to delete. Here also we are going to delete our anti-resonance point. Here also we are going to delete anti-resonance point. Anti-resonance point that is coming at 8.15. This is your anti-resonance point. We just delete it. Okay. Similarly, we'll go for our XY data 4. XY data 4. Here also our anti-resonance point is coming at your 8.15. That also I'm going to delete. Okay. Again, there is some value. We can delete that value also. 84 is there, so we can delete that value, and we can delete that value also. Okay. So now here we have some data. Now what we are going to do, we are going to copy this data. Okay, we are going to copy this data. Okay, and we are going to see how the damping is affecting our steady state response. Our damping is affecting our steady state response. Damping is affecting our steady state response. Here, this is corresponding to third data, that is XY data 4, that is corresponding to our 0.1 damping factor. Okay, now what we are going to do, we are going to plot, we are going to plot the data. Okay, here what we are going to do, here we are going to select this is your X and Y value only of your okay. That is corresponding to undamp. We can delete that part, delete the series. Okay, okay. That is your XY data set. Okay, so here we have one data. Next we can add here. Now you are selecting your data corresponding to undamped system. You are selecting the data corresponding to undamped system. Okay. If you select the data undamped systems, what is going to happen? Here you can see that magnitude of undamped displacement is coming quite high. That is your, and the range of e to the power 13. Okay, that is quite high. So what I am going to do, I am going to delete that for the data. Okay, that is corresponding to our undamped systems. Here you can see this data is corresponding to our damping factor at 0.01, and next we have damping factor data corresponding to damping factor 0.05, and third one is corresponding to damping factor 0.1. Okay, now here you can see how our damping is affecting our steady state response. Okay, so this is the way damping is affecting our steady state response. Here you can see the magnitude is coming in the range of 0.06. But if you have undamped systems, basically our displacement at that natural frequency is quite high. Okay.
In this class, first we have learned how to obtain our time response. Then we have learned how to perform our modal analysis. And then we have learned how to perform steady state analysis. Okay. And initially, we observe the time response, basically response where displacement is a function of time. And here in the steady state response, what we observe that our magnitude of the displacement is a function of frequency. Okay. And in the modal analysis, we have observed that we can only find frequency and the mode shifts. Here also you can observe in the modal analysis, we do not have any information about the damping because the equation we are solving for modal analysis do not include any damping. So we are getting real value of your eigen solutions. We are getting real frequencies and we are getting real mode shifts. Okay. The next video, where you want to see how the damping is affecting our time response, how we can perform dynamic explicit analysis, how we can perform dynamic implicit analysis, and how our forcing functions is affecting our displacement and how damping is affecting our displacement. That are going to learn in the next video. I hope you get some idea. Thank you.